Welcome. This video will discuss the concepts presented in Chapter 9, Section 10. Chapter 9 is based on the synthesis of different compounds using alkynes as a starting material. Earlier in the chapter, we explained the mechanism for converting terminal alkynes and acetylene molecules into anions at the terminal carbon. This process of deprotonation of an alkyne requires a base stronger than hydroxide, such as sodium amide. So, if we start with a terminal alkyne, such as this, in solution with sodium amide, we have a proton transfer causing a deprotonation of that hydrogen, resulting in the alkynide ion, essentially making this compound into an ion that is much more reactive and useful in different synthesis use cases. This section explains the alkylation of terminal alkynes, or alkynes with one carbon that holds a single bond with a hydrogen as well as its triple bond. Alkylation proceeds through an SN2 pathway where a deprotonated alkynide ion performs a nucleophilic attack on the carbon bonded to a halogen in an alkyl halide. The result of this reaction is the addition of an alkyl chain to the terminal alkyne. The mechanism is as follows. So, starting with a terminal alkyne in solution with sodium amide, a deprotonation will occur, producing an alkynide ion. This alkynide ion will then be put in solution with an alkyl halide, such as this, and the lone pairs will attack this carbon in a nucleophilic attack, pushing these electrons onto the iodine. That will produce this alkyne with the alkyl chain attached at the site of the alkynide ion. The alkylation of an alkynide ion, shown in the previous example, can only occur with a primary alkyl halide. When a secondary or tertiary alkyl halide is used, the result is an elimination reaction rather than a substitution reaction. This is due to the fact that this alkynide ion functions as a base instead of a nucleophile when in solution with a secondary or tertiary alkyl halide. This causes the alkynide ion to perform proton transfer on the alkyl substrate as well as pushing the leaving group off. So starting with a terminal alkyne in solution with sodium amide, as always, we have a deprotonation producing an alkynide ion, which then is put in solution with a tertiary or secondary alkyl halide, which causes a proton transfer deprotonation on the alkyl substrate as well as loss of leaving group. This results in resynthesis of the starting alkyne as well as the production of this alkene. The uses of this alkylation in synthesis are great. This is shown best in an acetylene compound, which can be deprotonated twice, giving two locations for alkyl groups to be added. This is powerful as these two alkyl groups can be different from one another. To perform this, we must go through 4 steps: 2 deprotonations and 2 alkylations. Each deprotonation must take place one at a time before each alkylation. The deprotonation and alkylation cannot happen at the same time since the alkyl substrate used in alkylation and strong base used in deprotonation will react with each other and give many different substitution and elimination reactions. The double alkylation of an acetylene compound with 2 different alkyl groups will now be shown. So we start with an acetylene compound in solution with a strong base, in this case sodium amide, which deprotonates one of the terminal carbons, giving an acetylene ion. This acetylene ion then does a nucleophilic attack on this alkyl substrate, causing the leaving group iodine to leave, and the carbon which was before attached to the iodine is now bonded with the terminal carbon. Moving on from this point, we must perform another deprotonation to produce an alkanide ion, which can then perform another alkylation step. So, a deprotonation occurs here, producing an alkanide ion, which then is put in solution with this alkyl substrate and performs a nucleophilic attack once again on the electrophilic center of this alkyl substrate, causing the leaving group to leave and bonding this alkyl chain onto the carbon, producing this alkyne with two different functional groups on either end.